Welcome to our next lecture in the series on condensed matter theory. In this video I want to have a look at some examples and comparisons to experiment of ligand field theory calculations. And for this we'll have a look at nickel oxide and copper oxide as the examples. Nickel oxide is one of the example correlated materials where you have multi-orbital effects as well as the oxygen and the nickel atoms playing a role. Copper oxide is one of the exemplar materials for the high temperature superconductors, where you have similar crystal structures that we have in those materials, but then you get high temperature superconductivity when you dope these materials. So if we look at nickel oxide, then within ligand field theory we approximate the crystal by a single atom and the surrounding ligand atoms. Of course, this is a severe approximation. You can't do conductivity with this, but you are able to look at the local excitations. And you only get away with this because these are highly correlated insulators. We will extend these models later with the use of dynamical mean field theory to go to lattice models. But let's first have a look at the possible local states. Our oxygen is completely filled, the nickel has locally 8 electrons, it's 2 plus giving up the s electrons, and we have locally 5 orbitals with 8 electrons. 5 with spin down, 3 with spin up. That gives you an SS1 state such that you have in your multiplet S set is 1, 0 or minus 1. Then because of the crystal fields, you split into the T2G orbitals that are completely filled and the EG orbitals that have 2 electrons in the ground state. And then of course we can make excitations from there that we'll want to have a look at as well. So those are the T2G and EG orbitals. In density functional theory calculation, you'll find your oxygen P bands, your nickel T2G and your nickel EG bands, representing the similar structure as we saw before for a single atom, but now with dispersion. Then of course the material is a real insulator in the experiment, but nonetheless the potentials are okay, such that we can use them as we've shown in the previous video to get your Barnier orbitals, and based on that get a many-body Hamiltonian that includes the on-site energies, the hoppings between ligand and d orbitals, the on-site energies of the ligand orbitals, and then your spin-orbit coupling and your Coulomb interaction. And it is of course this Coulomb interaction that makes the system so interesting. Now let's have a look on a few possible excitation spectra that we can make and how the excitation spectra are influenced by this local Coulomb interaction. And the first excitation spectra that I want to look at is just your one particle Green's function, or the photoelectron spectroscopy, where you remove one of the d electrons for your system and see how your system reacts. And on top we have the experimental spectrum. And what you would expect on a single electron theory is that you can remove an electron either from the E2G or T2G or EG orbitals, and then of course also from the oxygen orbitals. Now at these photon energies, the cross-section for removing an electron from the d orbitals is much larger from the oxygen orbitals, such that you are highly sensitive to the d partial densities of states. Now if you look at the density functional theory densities of states, then you indeed find that you have here your d orbitals, and then you have the hybridization between the d orbitals and the oxygen p orbitals. This is your oxygen p densities of states, this is your d densities of states. But you also see that it is a metal, so that you get a metallic state here, whereas in the photoemission you are not able to remove electrons at 0 energy. It always costs some energy to remove these electrons, and it's an insulator. And furthermore, well, the width that you have here doesn't compare to the width we have here or the splitting we have. So it doesn't really seem right what we have. You can modify your functionals to make the system insulating. The LDA plus U is such a modified functional, but even that doesn't really improve the description of your system. Now if we go to a ligand field theory calculation or a cluster calculation, then you get a discrete set of states, and those are the discrete set of states indicated here below that belong to different atomic terms that are further split by the ligand field. And now we get the local set of d orbitals where we have the excitation as well as the charge transfer excitations, and we see that at least you get a rough understanding of where your peaks are. Now these are calculations where the parameters are not taken from density functional theory but optimized, and then different people find different optimum set of parameters, and you see that, well, Van Elp had his charge transfer slightly too high, Fujimori had that better, then the intensity of peak B nobody had really good, and there's some additional intensity in between. And now of course you can ask the question, is this because people didn't take their parameters completely right, or is this because nickel oxide is a solid and not just a single atom? So for that we can have a look at really single atom calculation and experiment where you put a nickel impurity in MgO. MgO has the same crystal structure as nickel oxide, but the manganese atom has no d electrons, so that it's a wide band gap insulator. And now we put in a single nickel atom such that you locally really have a nickel O6 kind of cluster. And if you compare this now to a nickel with 6 oxygens, so your ligand field theory calculation, then you indeed find that it now compares much better to the experiment, just because, well, now the experiment is done in such a way that you reproduce the theory. You made the same approximations in your experiment as what you are able to do in the theory. Now the nice thing about nickel is that because it's only 2 holes, you can make your cluster bigger, so you can extend beyond the standard ligand field theory calculations, and you can put in cluster with, for example, 3 nickel atoms. And now you see that the agreement between the experiment and the theory for the bulk nickel is getting better. The peak B that we have here, that is absent for a single impurity, and in the single impurity calculation becomes visible when you go to extended clusters. So you see that with this you can reasonably well capture your 1 electron Green's function. There are of course limitations what you can do with a single cluster, but you understand where they come from. And you have well, this entire multiplet splitting plus your charge transfer excitations in there that you capture actually pretty well on this level of theory. Much better than you did on a just mean field theory level. Now, instead of looking at valence band spectroscopy, you can also make core level excitations. And the nice thing of core level excitations is that the different configurations now get different energies, because you change your effective on-site potential, because you change the number of core electrons. And here we look at an example of copper oxide, where you now see that you have a peak corresponding to the D10 configuration with a ligand hole, and you get a set of peaks corresponding to the D9 configuration. In the ground state, these 2 configurations are degenerate, so your ground state wave function is a linear combination of D9 and D10 ligand hole. Now we make a core hole such that here you have 10 core hole D interactions, and here you only have 9 core hole D interactions, and that splits the energy by a core hole D Coulomb interaction, which, well, is several electron volts bigger than the hopping amplitudes. If you just look at the integrated intensity here and the integrated intensity there, that tells you how much D10 ligand hole and D9 contributions you have to the ground state. But if you just look at the spectra, then you can also see that when you calculate those, you get reasonable agreement based on these ligand field theory calculations. When you make such a core hole in a p-shell, then the p-shell has strong spin-orbit coupling, such that you either have the p3 half core hole or the p1 half core hole, so your set of peaks is doubled. And again, here you see the splitting between the D9 and the D10 ligand hole configuration that were linear superposed in the ground state. Now you also see that you have the D10 configuration is very sharp, whereas the D9 configuration gives you, well, several internal peaks. And you should realize that you have here a Coulomb interaction between a hole in the P and a filled D shell, and there's only a single multiplet, whereas here you have a hole in the P and a hole in the D, and then there are many different multiplets, which you see now also arise in this spectrum. For the case where you have a hole in the p1/2 orbital, you should realize that your charge density of a p1/2 is cubic. You have a single hole in the D shell, and therefore the number of multiplets is just very small, related to the spherical charge density, and a single hole that has to be in the x squared minus y squared orbital to begin with. Yeah, so that's the core level photoemission, which allows you to look at the local charge fluctuations in these kind of materials, and also you nicely see which configuration has to be which configuration because of the multiplets that we have in our system. Now, instead of looking at one particle Green's functions or core level photoemission that tells you something about the charge fluctuations in your system, we can also look at low energy excitations. And because many of these materials are insulators, or better said, this level of theory only makes sense if you look at an insulator, we can have a look at low energy excitations inside the optical gap. So taking out an electron from one side and putting it on another side costs you a Coulomb energy U. That opens up a gap such that you become an insulator. But now you can take out an electron from one side and put it in a different orbital or with a different spin on the same side. And this gives effective low energy excitations. These excitations can actually propagate through your system, becoming magnons or DD excitations, orbitons within your solids. And let's have a look at DD excitations in nickel oxide. We saw before, experimentally, you have an optical gap of about 3.5 to 4 electron volt. So it takes 4 electron volt to take out an electron from one side and put it on another. But flipping electrons between orbitals should take much less energy. So these are transitions that you in principle could make with optics. A photon can make these local excitations, but one should be careful, because when you interact with a photon, you have to have a parity change in your system. You make excitations between even and odd states. And if you want to make a transition between two d orbitals by either flipping the spin or the orbital, then this is even to even, so that in principle they would be completely forbidden. Now you can always add a phonon that locally breaks the inversion symmetry, such that in optical experiments you do see these DD excitations, but they're very weak compared to the charge transfer gaps that have charge transfer excitations or Hubbard-U excitations that are much stronger. So there are other ways to make these type of excitations, and that is, for example, inelastic X-ray scattering. You can come in with a photon and go out with a photon, and then that photon loses part of its energy, and then you are allowed to make even transitions because, well, you absorb the photon and emit the photon, or you have an interaction via the A squared term, where you have just the inelastic scattering or the bouncing of a ball that can transfer some of its energy to your system. Now, if you look at such an experimental spectrum, then you see that you have 3 clear peaks in your excitation spectrum. And we can also look at the theory. And the theory of nickel, we have locally 3 electrons, 2 holes, 8 electrons. That gives you a triplet F ground state and a triplet P excited state. Then the triplet F splits into a triplet A2, which is the ground state, a triplet T2, which is the first excited state, a triplet T1, which is the second excited state, and then the triplet T1 coming from the triplet P atomic state. Photons interact with angular momentum but not with spin, such that the excitations are only allowed between triplet states, and that's indeed what you see. You do not see the singlet states that you also would have in your system, but just the possible triplet excitations. So if we now want to understand why we see 3 of those, we can start from the atomic state where we have 8 electrons in our D shell. Then in a cubic crystal field, they split into the T2Gs and the EGs. The T2Gs are filled and we have 2 electrons or 2 holes in the EG shell. That makes you a triplet, and the T2G and EG 1 particle states. Now the first peak you can understand on a mean field level, where you just say I have my orbitals in this filling, I take 1 electron out of the lower orbital and I place it in the upper orbital. That gives you an energy excitation that corresponds to the energy difference between the 1 particle T2G and EG orbitals, and that sits at 1.1 eV. And that's exactly the energy that you see in the experiment. So this you can understand on a mean field level. Then we can also understand the last peak that we have, and that is related to the Coulomb interaction. If you think of your orbitals, now we make a hole in the YZ orbital and excite this into one of the T2G orbitals, then we can either excite it into the dz square or to the x square minus y square. And Coulomb repulsion is smaller when electrons are further apart. If you now look at the hole that we have in our xy orbital and the electron that we added in the x square minus y square or z square orbital, then you see that in one case they are planar, they're close to each other. In the other case, one is pointing out of the plane, the other is in the plane, so these are further away from each other. This gives you an energy difference between having the hole in the T2G and the electron in the EG close to each other, or the hole in the EG and the extra electron in the T2G further away from each other. So that explains you the third peak. If you look at a hole in the T2G and a hole in the EG, when the 2 holes are close to each other, you have a high energy. When the holes are further away from each other, you sit in the low energy state. Now, if you say, well, I'm going to work with a potential, but I say when I make an excitation, I allow my potential to change. So you make a time-dependent potential. You would be able to explain 2 out of these 3 peaks. But the experiment still shows a third peak. And in order to understand the third peak, you really have to realize that the T1 states are not single Slater determinant representable, but are many electron states, and you have to go beyond mean field theory. And indeed, a Ligand Field Theory calculation captures this, where you represent your local states as sums over Slater determinants. Now you can understand this second peak by saying I'm taking out 2 electrons from the T2Gs and place 2 electrons in the EGs. That's also roughly the energy where you sit. And then of course you have the mixing between Coulomb interaction and a 2 electron excitation. Now when you describe something like this as a 2 electron excitation, you should be really careful, because the photon still comes in. It only makes 1 electron excitation. It excites 1 T2G electron into the EG orbitals. But then the Coulomb interaction kicks in, and the Coulomb interaction allows you to scatter, such that when you change 1 electron, the second electron is correlated to this and also changes its orbital from T2G to EG. So one excitation is because of the photon, the other one is because of the Coulomb interaction between the electrons. And you truly have to solve a many-body system to understand and capture this. So with that, I hope to show you a few of the effects that we have and that we can capture on a level of ligand field theory, both for the photoemission spectroscopy, the core level photoemission spectroscopy, that becomes really sensitive to the configuration mixing that we have, as well as low energy excitations inside the gap, either the D-excitations or Magnon excitations, spin flips. Spin flips you would measure in an ESR spectrum or in a inelastic neutron scattering, whereas the D-excitations you can measure with inelastic X-ray scattering and nicely see what your energy states are in your system. Thank you very much for your attention. We see each other later. Stay healthy.